Hi everybody, this is Mr. Folly, and welcome to our last, wow, that's a good one, podcast of this chapter and of this test. The test is over chapters 10 through 12, so you want to make sure that you remember that because 3/4 of that was pre-semester break. The first thing we're going to do is look at graphs with rate of change. So basically we're doing a bunch of graphing interpretation that goes along with it. Collision theory we already mentioned, just want to reinforce it again, and we're going to apply it a little bit later. And then energy diagrams of kinetics, that's the little woo, or the little woo that you remember from way back when. Boltzmann diagram, remember that's the temperature and the number of particles things for activation energy. Factors that contribute to the rate, we're going to talk about those things, and of course relate them back to the collision theory. And concentration changes do not always have the same effect, and why. I was told some of these pictures in the best way possible. This is from your book. We're in chapter 12. It's probably 12.1 somewhere in there. I usually put the title on there, but I didn't. But what you can see happening here is, let me make my pen a little darker, is you've got one thing that's decreasing at a constant rate. You've got another, not a constant rate, pardon me, and something else that's increasing, and something else, again, that's increasing. And this should tell us enough about a reaction to figure out what's going on. So my axes down here are time in seconds, and concentration in molarity, or the y-axis. Well, it is the y-axis. So what happens is you start off with something that has a high concentration, and it goes down. Guess what? That's your reactant. Then you have something else that starts with a 0 concentration or a very low concentration, and that's going up. That's a product. Here's another product. So the things that start off very low are at 0 and increase are products, and things that start high and decrease are reactants. Typically what these graphs show is in the end, sorry for not changing my colors here, they end up hitting a plateau where they do not change concentration anymore. That does not mean that things have stopped in most cases. That means that you've reached equilibrium. All right. So when you have more than one reactant, for example, these things come up in exactly doubling amounts. So here, or it should be or close to it. So this you can determine if it's 1 to 2, 2 to 3, 3 to 4, something like that, based on the coefficients. So the blue line that I drew, for example, would have a, let's see, when this is about 0.25, this is about 0.05. Okay, so this is probably about a 2 for a coefficient because it's twice as fast, and this is a 1 for a coefficient. So you can determine the rates of change. So what else do I need to do? I think the next slide asks those questions. I wanted to make sure I rest with that. What are the reactants? We talked about that. What are the products? We talked about that. Coefficients? We talked about that. What happens when the graphs have a slope of 0? That's equilibrium. What are the reactants? The reactants are the ones that start with a high concentration. And what are the products? Ones that start with typically a 0 concentration. What are the coefficients? You can determine that by looking at the ratios of change. Why do all the slopes reach 0 at the same time? Because reactants and products have to reach equilibrium at the same time. You can't have like the reactants in equilibrium and not the products. I want to go back to my smaller pen now. All right. Here are the energy diagrams that we've done. A whole bunch in Excel, but we tend to forget them pretty quickly. We have our reactants here and our products here. This is the heat of the reaction, our delta H value right here. So notice how the reactants have a higher energy than the products. So that means heat is released, which means this is exothermic. And the products are energetically more stable than the reactants because they're lower energy. And again, think of, shaking the baby. Don't shake the baby. Don't shake the baby. You want to be lower energy. Your reactants are here, then they reach a higher energy state, and this right here is called a transition state or an activated complex. or an intermediate. When we did our reaction mechanisms, we called them intermediates. Okay? And that's about it. There's one other thing I want to show you. I'm going to show you endothermic here in a minute. But a graph can have a bunch of those. Each one of these peaks would be an intermediate, and it could imply how many steps the reaction has. Now that's an obscene number of steps, but you get the idea of how that happens. And you could have more than one step based on the number of hills, and it'll tell you the number of transitions. So the next one coming up should be the endothermic reaction. And it is, same basic idea. Notice your activation energy is from a reactant to the peak, not from the highest one to the peak. So the other thing is delta H. Notice in this case delta H is going up, so it's positive, so it's endothermic. Again, you have a transition state, and again, you could have several energy hills as long as it's endothermic, just because the reactants and the reactants are lower than the products. A catalyst changes the rate by lowering the value of EA. This is the important part. By changing the mechanism. And those are the mechanisms we've been dealing with before to rate mechanisms for different things. It lowers the activation energy by changing the mechanism. It takes a new path. So basically what happens is your hill is different down here, and that also means you probably have a new transition state. I guess I should have made that a star, like the other one. In order for action to occur, there must be a collision with enough energy and the right orientation. And we need to explain how those factors contribute to how these factors contribute to the rate. Temperature. If you increase the temperature, you want to say there's more collisions, and that's true, but that's not the main thing. There are more effective collisions, which means there are more collisions with enough energy. Okay? And you need to say more collisions with enough energy. And that's a really tough barrier to get, the activation energy. Increase pressure. If you have a higher pressure, you're going to have more collisions. Nature of reactants. Depending on the nature of reactants, that will tell you how effective the collisions are. This determines the mechanism, which determines EA, which determines the energy needed. I said that really quickly, so you probably want to rewind that. Concentration is a sometimes change because, remember, it depends on the order. But it's a sometimes, but usually it increases the number of collisions.
Good morning, Elsie. Please
Okay, so you have to state the parts of the collision theory with either there have to be collisions with enough energy and the right orientation. Catalysts usually they don't necessarily give you that better orientation. And this is going to be a Boltzmann diagram that will show you how temperature affects the energy of these things. So here's your activation energy. You need to have that much activation energy for your reaction to take place. So I always like to think of a reaction like hitting a home run. Not just hitting a ball, hitting a home run. So if you want to hit a home run and you're so weak you can't hit the ball out of the infield, then you have issues. You'll never have a successful reaction. But if you're stronger, that means you have the potential. So if you are unbelievably, monstrously strong, then you have at least the potential to hit a home run. So this T2 would be someone who is unbelievably, monstrously strong, say Lauren, and this would be somebody who never actually gets any strength or builds up any strength and sits around and plays World of Warcraft all the time. So he would barely ever be able to hit a home run. This is just a graph showing the same thing. AP likes to use one or the other. And remember, both of these, the graph in the last slide and this slide, are both called Boltzmann distributions. And they're talking about the temperatures of different. And remember, the colder is higher. This was shown better on the other one. Colder is higher, and hotter is lower. And the temperature is basically the peak of the graph. So you can tell which one's hotter by looking at how far the peak is. Another interesting graph that's popped up once or twice, this right here is the activation energy, and if you kind of turn it on its side, you can see that if you have a catalyst that lowers the activation energy, then that means that the number is over here and it's affected that way. So that's one of those interesting type dealies. Concentrations effects are not always the same, and I mentioned this briefly before. Concentrations effect depends on the mechanism. The concentration only matters if it is in the slowest step or an equilibrium step. So basically it depends on the rate law. Yay! Let's review. You have to be able to interpret graphs of rate. So that was the very beginning thing that we did. Coefficients affect the relative rate. So what that means is if a reactant, if I have two reactants yield 3 products, if I tell you that 10 reactants disappear, that means I should have 15 products up here. There's a question or two in that first worksheet you did where you had to be able to make a relationship between the coefficients and the amount that changes for the same unit of time. Zero slope is equilibrium. Reactants have amounts in the beginning, products don't. You should be comfortable with those reaction hills and catalyst diagrams, and those are the woo or the woo things. And remember, your activation energy is from the reactants up, not from the lowest point up. Explain that rate is changed by pressure, more collisions, temperature, more effective collisions, concentration, more collisions, catalyst, changes the mechanism so that it requires less energy typically, or more effective collisions. That would be it. Toodles. See you tomorrow.